keep in mind we were able to derive our formula by using the acronym or the mnemonic device SALLY, and means we subdivide the interval, we approximate, and add, take to the limit, and then identify an integral from the Riemann sum we come up with. Okay, so imagine we want to find the volume inside f of x and outside g of x when that whole thing is rotated about the x-axis. So you imagine this region is rotated about the x-axis. You can see it's got a hollow piece on the inside. And so the question is, how do you find the volume of such a thing as that? I have a pretty reasonable picture of it here, I think. That's what we're trying to find the volume of. I couldn't find a really good way to shade that, but it's in between the hollow part here and the outer part, which is shaded in with a blue border. That's what we're trying to find. So we'd subdivide it first, and here I've subdivided it up into washers. You see, washers. These are washers, right, that would approximate the volume. So we subdivide it first. We approximate, well, let's look at just one of these washers. By the way, of course, there's, we're going to essentially, there's going to be an infinite number of them. We approximate this. Well, it's actually not a washer in the first place because this edge isn't necessarily squared off. It might be slanted like this, but we're going to approximate it with a washer. And you may recall way back when we said, well, the volume of a washer, this is a washer on the other side, but is pi times the outer radius squared minus the inner radius squared times the height, the thickness of the washer. So back to our problem here. The volume of one washer is pi. I should write that. Volume is approximately equal to pi times the outer radius, which is f of c sub k squared, minus the inner radius, g of c sub k squared, and all that times the delta, the thickness of that washer, I want to say times delta x sub k. And so if we added them all up, then all of these washers add up as the following. Oops, and here I left out my delta k. Found myself a typo there. Delta x sub k. There we go. Whoops, typo again. There, I think I got it now. There, yeah, that's it. I don't need the parentheses there, so I'll delete that. Okay, and we could factor the pi out of that, but now you say, well, the volume would be exactly equal to the limit as a maximum of those delta x of k sub k's approach 0. And since I'm calling it I here, I guess I better call it I here. And whoops, how could I forget my delta x sub I mean, subscripting variable is a subscripting variable, so it doesn't matter what I call it as long as I'm consistent. Okay, there we go. Now, so here is the volume of that, and I factored the pi out, and I can identify this with this maximum as a Riemann sum with the pi factored out. Actually, I could have put the pi out in front of the whole limit symbol there if I wanted to. So anyway, I can identify now my integral, which is pi times integral from a to b of f of x squared minus g of x squared dx. I didn't show you the a and the b, but if you go back to the beginning, you can see that that was borders for our region. And so that is our formula for finding the volume of a solid of revolution about the x-axis using the method of washers.